Bear with me here. I'm not prepared at all. Just gonna roll. Anyway, starting now. So this is my presentation on gravity. So, gravity all started off with Isaac Newton and his classic apple fall on the head thing. So I think you guys have all heard that story. But basically, from that he developed the concept that all bodies in the universe somehow attract one another. And eventually he came up with the Universal Law of Gravitation, which basically says that the force of gravity between any two objects is equal to some constant g times the mass of one object, the mass of the other object, over the distance between them. So basically what this is saying is that if you have one object, like mass 1 here, and it's got a mass of 50 newtons, and you have a second object with a mass of 1 newton, they're going to exert a force on each other, and because this one weighs more, it's going to exert a stronger force pulling this one in, but this one's also going to exert a force on this one, pulling it toward it. And this happens with every body in the universe, from an ant to another ant, to us to an ant, and even the sun to an ant. So from here we kind of started developing more and more applications of gravity that would kind of answer the questions of all the astrophysical anomalies in the universe. And this kind of started off with the idea of orbits. So at some point in time, people decided that the Earth isn't the center of the universe, and the sun might be the center of the universe. So that was the heliocentric principle. And they decided that the sun is the most massive object we have around us, and all the objects near it are going to orbit it. And that has now been proven true. But with the advances in modern telescopes, we can find new supermassive objects like galaxies. And we now know that solar systems are just one little unit inside of galaxies, and they all orbit the center of a galaxy. And on an even larger scale, we find that galaxies even orbit each other in whole galactic systems. And so you see here, this is actually each one of these light regions is a solar system orbiting the galactic center. And if you had more galaxies, you'd see that each galaxy is going to orbit each other galaxy. And it forms this crazy set of orbits that goes from the smallest thing in the world, from an electron, all the way up to galaxies and galactic clusters. But anyhow, so that's the basic concept of gravity. So now we go into the effects of gravity. So a common effect that we're all familiar with is the moon and Earth. Earth actually, a lot of people don't know this, but Earth has the largest moon in our solar system. And so Earth's moon exerts a fairly significant gravitational force on Earth. And that's the main cause of the tides. So if you see this picture here, here you have the moon. So the Earth is exerting a significant gravitational force on the moon, causing it to orbit. But the moon is also exerting a gravitational force on the Earth, causing tides. And so what we see is the water on one side of the Earth is actually pulled toward the moon. Then the Earth itself is pulled toward the moon, and the water on the other side is kind of left there. And so what you create is this large tide on the moon side, and then a smaller tide on the opposite side, and that's all just due to the gravitational effects of the moon. And on an even larger scale, if you look at Jupiter and its moon Io, that's I-O, you have enormous gravitational effects because Io is one of the closest moons to Jupiter. And Jupiter exhibits the same kind of tidal effect, except it's so powerful that it can actually move the rocks on Io's surface. And even though Io is millions of miles, well, hundreds of millions of miles from the sun, Io is still molten because the gravitational effect causes so much friction that actually there's so many volcanic eruptions on Io. If you look at it, like click on that picture there's so many volcanic eruptions. Each one of these spots is a volcano erupting. That's because Jupiter is actually exerting a strong enough gravitational effect to pull the magma out of Io's core and onto its surface. And every day Io's surface completely changes just due to these volcanic eruptions. So now if you go to an even larger scale, the supermassive scale, you can look at things like black holes. So basically the concept of a black hole is if you think of a trash bag, and you're holding it taut in front of you, and you put a marble on that trash bag. It's going to create a slight depression in it. And let's say then you take a basketball, it's going to create an even bigger depression. But let's say you took something the weight of a basketball and made it the weight of a marble. Now it's going to have a lot of weight in a very small region. And it's basically going to be bending that trash bag extremely deep. And so the whole concept of gravitational orbits is that in the giant trash bag of space, if this is the sun, it's creating a large dimple that then each planet is going to rotate around it. And so if you have something like a black hole, which is incredibly dense, it might have the same amount of mass as the sun, but it's concentrated down into maybe a mile across instead of 90 million miles, wherever the sun is. So now you're going to have a huge concentration of mass at a very small point, and space's trash bag is going to be bent like this, and it's going to create this vortex that's so strong that instead of things orbiting it, they're just going to kind of spiral into it. And once they reach a certain point, they're going to be moving so fast toward it that they actually can't escape. And that kind of brings us to the idea of escape velocity. So every object in the field of gravity has something called escape velocity. And that's basically the velocity at which something needs to move to escape its gravitational field. So with the Earth, we think of escape velocity as like a rocket blasting off. So when a rocket blasts off, it has a velocity fast enough to actually overcome gravity's force and leave Earth. In terms of a black hole, the escape velocity is actually faster than the speed of light. And the speed of light is 3.08 times 10 to the 8th meters per second. So, that's an incredibly fast escape velocity. And that's, nothing can exceed the speed of light. So even light cannot escape a black hole, and that's why they're black, because no light is emitted. And so that kind of wraps in the whole idea of, gravity on a tiny scale to an extremely large scale. And from gravity, we see all sorts of effects, from absolute destruction. You have let's say the Earth approached a black hole, it fell, and it would be absolutely decimated. But you also have creation from gravity. And that's kind of the coolest thing about gravity, is that it's so powerful that it can actually drive the creation of new stars. And when you have a new star created, you might have new planets created. When you have new planets created, you have the opportunity for new life. So, gravity is kind of something that, it's just a theory, but it's a theory that seeks to explain a huge part of the universe. So it's pretty cool.